Okay, this is scenario one for confidence interval. And once again, we're going to start off just like we have before. We define the parameter, but in this case, it's mu d, which is the mean difference. So we're going to say let mu d equal the mean difference. Where it says write the conditions, we're just going to continue writing assumed. Don't have to worry about it. Want to talk briefly about our formula. We were working with a t-test where x bar plus or minus t star s divided by the square root of n. But now we're working with differences because we have two sets of data, two data lists that we're subtracting and each one individually. So that gives us a difference. And otherwise, it's the same thing because the averages of the differences, the standard deviation of the differences, and then the sample size, and of course, t star. We're going to go, our conclusions are set up the same way. So basically, the recipe for success is almost exactly the same as we had before. And we're going to continue with the same scenario one that we did for the hypothesis test. And we're going to rerun that. Well, I'm going to try to do that as soon as I clear out my calculator. Okay, so one indicator of physical fitness is resting pulse rate. 14 men volunteered to test an exercise device advertised on television by using it 3 times a week for 20 minutes each time. The resting pulse rates in beats per minute were measured before the test began and then again after 6 weeks. So basically, we tested them before they started exercising, and then after 6 weeks of exercising, we measured it again. Fun fact for all of you who are interested, these 14 kids were the first boys that I taught AP statistics. So they came from my AP stats class and were in the first AP stat class that I had. They were the first 14 guys that I was able to teach at Reagan High School. So create a 95% confidence interval for the mean difference and explain the meaning of the confidence level. So basically, Alec was measured before the 6 weeks exercise program and then again after. Trip was measured before, then again after. And what we're going to do is, we've noticed each one's been measured twice. We're going to go ahead and subtract those differences, all right? And sometimes they're going to be positive, and I think somewhere along the way we have a negative. But regardless, yeah, we have a negative. Someone actually ended up being, their pulse rate was higher. But we're going to take a list of these and we're going to create a 95% confidence interval. To do that, I need to enter this data into L1 and L2. If you watch the scenario one video, the hypothesis test, you've already done this. The first thing we need to do is define our parameter. Let mu d equal the true population mean difference in resting heart rate before minus after. It is critical that you tell me which way you're subtracting. Technically, you can go in either direction, but we went before minus after. And you always have to say which way. And it's going to change whether you end up with positive numbers or negative numbers, whether you do that. And in this case, if we started off with a before pulse rate of 80, we hope it reduces. It got better. So in that case, we should end up with 80 of 72 should be a positive number, because 80 minus 72 is 8. Because we're hoping it'll reduce, and if it reduces, that means we have positive numbers. But that's okay. Conditions. We don't have to write them for this class. I do have them for those of you who are interested. We need to have a random sample. We need to have n is less than 10% of the population. And the difference in pulse rates need to be independent. And of course, we need to draw our box plot. The next thing we need to do is write out our equation. So these you can just write assume on. But when we write our equation, we have x bar d plus or minus t star SD divided by the square root of n. The bad thing is I don't have all that information. So I'm going to need to find x bar d, SD, and I need to find n. And then ultimately I'm going to have to go back and I'm going to have to calculate T star. All right, T star is going to be based on 95%. So here's the way I have to do this. First off, I need to go to stat edit and enter my data. So there's my list of data. And basically I put the befores in L1, the afters in L2. It's all entered there. I really don't want to subtract this by hand and do all the averages. So I'm just going to go arrow up to the top of L3, make sure it's highlighted up at the top, and be careful what I say. We're going to go second 1, which is before, minus second 2, which is after, and that populated. Then I'm going to go stat test, and I'm going to go ahead and run this thing. Well, we're going to use a t interval because it's a t statistic. And the reason it's a t statistic is because we're using the standard deviation of the sample. And we press enter. If you have stats highlighted, you need to arrow over to the left so that data is highlighted and press enter. You may have second 1 listed. We need to change that to second 3. So second followed by the number 3. And that happens, press clear, then second 3. There you go. And we want a 95% confidence level. And we're going to get more information than we need at this point. So we can go ahead and write down the 1.2761. And I'm just going to go ahead and do that. I'll use it later. That happens to be the actual interval. And then I also have 3.8667. So I wrote those values down, but also I ended up getting my X bar, which I need. So X bar is 2.5761. And I 2.571, I'm sorry, 2.5714. And our SD is 2.2434. And we already knew that we had 14 pairs, so N is 14. All right, while we're here, let's go ahead and calculate our T star. And I probably should rewrite that, but it's 2.5714. 2.5714. Our T star, clear. Second vars, inverse T, parenthesis, 1 minus 0.95, close parenthesis, divided by 2. Degrees of freedom is 14 minus 1. Press enter. And we end up getting a T star equals to 2.1603. All right, so there's my T star. And now that I have X bar, S, and that, I can fill out my equation. So filling in, we're going to have 2.5714 plus or minus my T star value, 2.1603. Standard deviation, 2.2434 over the square root of 14. Now, we needed to make sure, and I did not write this down, my degrees of freedom are 14 minus 1, which is 13. And I need to go back and check my T star to make sure I did that. Second vars, inverse T, and sure enough, I have 14 minus 1, all right? So I wasn't sure I'd done that. 14 minus 1, or just putting in the 13 like I just changed it to, should give me 2.1603. We like to work with positive values, makes life easier. Well, when I ran this, not only did it give me the information to fill in the equation, it also gave me my lower bound and my upper bound. So what can we say? Well, we can say we are 95% confident that the true population mean difference, because we're working with a paired, in resting heart rate or in pulse rate, before minus after, we always have to say which way we subtracted, lies within the interval 1.276 to 3.867. We can also say that in repeated sampling, we expect that this method will capture the true population mean difference in resting heart rate before minus after 95% of the time. Note, 0 does not lie within the interval. All right. Therefore, we are 95% confident that there is a difference in that, not that there's a difference. Well, we can say that, but it's better yet to say that resting heart rate was reduced. We can say resting heart rate was reduced. The program worked. All right. The reason we know it worked is because we had, on this case, because we have positive values. All right. That closes this video. Thank you.